Good morning. This is Jerry Tuttle, and I'd like to talk about the project I did for General Electric on predicting its loan defaults. This is quite an interesting project. It was more difficult than I expected, but I hope I produced a useful result for management and the company. First of all, General Electric certainly has a proud history that goes back 100+ years, back to its founder, Thomas Edison. Thomas Edison, a genius inventor, um, has museums in both New Jersey and Florida. I visited both of them. If you have an opportunity to visit one or the other, I certainly recommend that you do. So GE has a 100+ year history. It has a well-recognized brand worldwide. For many years, it was one of the largest and most profitable companies in the United States. But unfortunately, in recent years, GE has performed poorly and was removed from the Dow Jones Index. So let's talk about the GE Credit Profit Center. GE offers credit to personal customers, but unfortunately, some portion of them don't pay back their loans. And in fact, in the data we looked at, 30% of customers defaulted on their loans. And that can get expensive. The average amount of loan in default was $3,900. Then there's an additional 50% overhead cost of those loans. So per 1,000 customers, that's a cost of defaults of $1.8 million. And that's just per 1,000 customers. And it's been said a million here, a million there. After a while, these millions add up to real money. So we hope to design a data analytic solution which will predict 70% of these defaults and save the company quite a lot of money. So we were given a data set of 1,000 GE customers, and the first task is exploring the data. We looked for duplicate records. We didn't find any, but it's certainly always a good exercise to make sure there are none. We looked for missing values, which can be either NAs or blanks, so we did look for both. The data dictionary told us that all the variables were numeric, but upon further investigation, many of them were really categorical data and therefore factors. We looked for some unusually large values of data, greater than 3 standard deviations from the mean, which we termed outliers. We looked for gaps in the data, such as, for example, if a whole range of values was missing. We looked for correlated variables. We correlated both the independent variables against the dependent variable default, and we correlated the independent variables among themselves. We also looked for ethically and illegal variables. I realize this is somewhat of a controversial subject, but our contention is that the data analyst really ought to do his or her best to protect the company from bad publicity and or illegal activity and fines. We believe that some variables are definitely illegal based on federal statutes and should not be used in this study, and we eliminated them. We also transformed some variables. The checking and savings account variable had a factor level for no account that caused problems with the other factor levels, and so we transformed those variables into variables that we thought made more sense. We did lots of plots. We plotted histograms of all variables to check for missing ranges of data. Uh, Here we're plotting distributions of some key variables for both the non-defaulters and the defaulters separately. So before doing any real analysis of the data, this gives us some idea of some of the variables that differ significantly between the non-defaulters in red or 0 and the defaulters who are ones in blue. So let's talk a little bit about logistic regression. Some of you are familiar with this and some are not. This is an extension of linear regression, although linear regression goes back to Gauss and others in the early 1800s. Logistic regression is fairly new, and I think only goes back to, say, the 1950s. So for logistic regression, we're given n independent variables x1 through xn, and a dependent variable y that has values 0 and 1. So the 0 and 1 are no default or default. Logistic regression fits a linear combination of these variables, then raised to the e power plus 1, then taking its reciprocal, and this function is set equal to p, where p is the probability that the dependent variable y equals 1. So p is a probability, and then with all probabilities we can calculate p divided by 1 minus p, and that's the odds ratio that y equals 1. We can also take the natural logarithm of this quantity. That's called the log odds ratio, and this gives us a smooth curve between 0 and 1, and that's important because our dependent variable only has values of 0 and 1. In linear regression, we would get a line that extends past 1 and past 0 in the negative direction. And with logistic regression, after we fit the curve and then we apply it to some new data, as we predict each new observation, if a new observation has a probability greater than 0.5, we're going to set y equals 1 and say that observation is likely to default. Otherwise, we're going to set y equals 0 and say that observation is not likely to default. So we started with 30 predictor variables, and we did numerous combinations of these variables in order to find the best regression equation. The first attempt used all 30 predictor variables, which with each attempt we measured each variable's significance and feature importance, which I'll talk about in a moment, and other model measures. We also attempted an interaction variable between the checking and the savings variable, and we settled on what we think is the best model using 15 of those 30 predictor variables. Then from the 15, we took one more shot at this, and we used a technique called stepwise regression. And in stepwise regression, we attempt all possible subsets of the original 15. That's a lot of subsets. I think it's 2 raised to the 15 power subsets, maybe with a -1 in there. That's a lot of subsets. We did not have any success with the stepwise regression. We did not find a subset of the 15 variables that performed better than the whole 15. So here is our final regression summary of the 15 variables. The 15 variables range from a negative checking account, low checking account, and so on, up to education and co-applicant. The first column is the regression estimate. The regression estimate in a logistic regression represents the marginal contribution to the log odds. So an increase in negative checking account increases the log odds of default. An increase in low checking account increases the marginal, increases the log odds by a lesser amount, and so on. So these are the marginal contribution to log odds. Standard error is a measure of the variability of the estimate. The z-value is the normalized value of the estimate by taking the estimate dividing by its standard error. Z-values are based on a mean of 0 and a standard deviation of 1. So a z-value of 7 is 7 standard deviations from the mean of 0. The p-value is then the probability of getting a z-value that extreme. And so obviously with a z-value of 7, the probability of getting a value that extreme is very, 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 very small. These asterisks represent the variables with very low probabilities of getting a z-value that extreme, and therefore these are very significant variables. Residual deviance is a measure of the unexplained error remaining after the regression, and AIC is a relative measure of fit, penalizing the regression for adding more variables. Residual deviance in AIC really make more sense when you're testing a lot of different regressions and seeing how they compare with each other. This is a graph now of feature importance. Feature importance shows for each of those 15 variables the relative contribution of each of those predictor variables in prediction. Again, negative checking account and low checking account have the highest amount of importance. Installment rate has the lowest contribution in the prediction. I found that somewhat surprising, but consulting the data dictionary, I realized that this installment rate variable is rate as a percent of income. It's not simply the interest rate, and so that's a little more complicated. But this shows the relative contribution of each of these, and perhaps this is of some particular interest to the loan underwriter as he or she looks at each individual case. Then we did a confusion matrix with a new set of data as we tried to predict default or non-default. So for every case, either the case does not default or it does default in actuality, and either we predict no default or we predict default. So every case belongs into one of these 4 boxes. This is called a confusion matrix. And as an analogy, you might think of a pregnancy test as a prediction of pregnancy. The pregnancy test can predict no pregnancy or pregnancy, and it can be accurate or inaccurate. So what does it mean for a false positive? A false positive predicts a pregnancy when in fact there is none. So the humorous example is the man who is predicted to be pregnant, but of course in actuality is not. So for our particular data that we looked at in order to test our regression equation, there are a number of measures of accuracy. What we don't particularly want to measure is how good we are at predicting no default when there actually is no default. That's not of great use to GE, the client. So instead we chose to look at the measure positive predictive value, true positives over all positives. That came out to 0.667. Not quite the 70% we were hoping for, but this is fairly close to 70%. And if we can achieve a 70% measure with the model in deployment, we'll be relatively happy. This is another way of measure performance of our regression. The confusion matrix is really at a single probability threshold. We talked about 0.5 as the probability threshold to decide between a prediction of no default and default. Actually, we could modify that threshold and pick other probability thresholds. That would give us a new confusion matrix every time we do that. And so this is sort of a plot of doing that. This is a plot of all probability thresholds from 0 to 0.9. Here we're measuring true positive rate versus false positive rate. This gives us a plot, and then we took the area under the plot, analogous to what might be done in integral calculus. The area under the curve is 0.731. The closer to 1, the better. And so again, we've got to measure better than 0.7. So this gives us some comfort that we have a fairly good measure of the overall accuracy of the model. This is what the production output will look like as the loan underwriter looks at each individual customer. So the loan underwriter will have a number of cases he or she looks at, and for each of these cases the regression model will give us a probability of default and then the model recommendation. And so with a 0.4 probability, the recommendation is approve the loan. At a 0.536 probability, the model recommendation is don't approve the loan. So this is a fairly simple output. Of course, the loan underwriter has all the information that he or she had before the model. We're not duplicating all that because he or she already has it. But this is some simple output for the loan underwriter to look at. We're certainly hoping that over time, the loan underwriter will agree with the model recommendation on the majority of loans. We don't expect the agreement to be 100%, but hopefully over time, the loan underwriter can spend more time on the loans where there's some disagreement than the ones where there's some agreement. So this concludes the formal presentation of how I constructed the model. I hope this model will be useful to General Electric and will save it a fair amount of money, which the stockholders will like because profit will flow through to the stock price, and employees will like because this profit for the profit center will provide more money into the bonus pool. I'm certainly available for any questions right now. If you have any after today, you can contact me at this email address. Thank you very much and have a good day.